All right, let's just jump right in. Welcome to another Explainer. Today, we're decoding the invisible rules that literally govern our digital lives. Every single day, we interact with countless systems, but we rarely pause to think about what actually keeps all of our data clean, organized, and secure behind the screens. Think about this for a second. Have you ever wondered how a massive online system, like a huge hospital network, can pull up your exact health records out of millions of patients without a single mix-up? Take platforms like Hong Kong's e-health system, for example. They digitize and securely share the medical records of millions of participating citizens. Now, they don't just dump all this information into a giant digital pile. They rely entirely on extremely strict data organization and control to function flawlessly. It's essentially the invisible architecture of trust. To understand how this magic actually happens, here is our roadmap for today's explainer. 1. Organizing the digital world. 2. Garbage in, garbage out. 3. The rules of data validation. 4. Check digits and parity bits. And 5. Storing and accessing data. We're going to trace the life cycle of a piece of data from the exact moment it enters a system to where it finally lives. Let's start with step 1, organizing the digital world. Because before any data can be protected or retrieved, it needs a proper, logical neighborhood to live in.
Think about how data breaks down from the top. It's a lot like a set of Russian nesting dolls. Imagine a massive database for a school. That database is broken down into smaller files or tables, like a table just for the students. Inside that table, we have individual records, which are rows of data representing one specific person. And finally, we break that down into individual fields, like a specific student ID, a name, or a class. It's a perfectly nested structure.
Moving on to step 2, garbage in, garbage out. So we've got this beautifully organized system, right? But what happens when bad data tries to crash the party? This brings us to the absolutely crucial garbage in, garbage out principle. It is a fundamental law of computing. If we feed a system completely unreliable or incoherent data, the output information it generates will simply be useless. The computer can only process exactly what we give it. And let's be honest, we feed computers bad data all the time. We're human, we make mistakes. First, you've got data source errors, like someone intentionally providing a fake email address. Then there are transcription errors, where data is just misread or mistyped. And finally, the transposition error. This one is so incredibly common. It's when you accidentally flip adjacent numbers around, instantly turning a standard $15 charge into a $51 nightmare. All right, step 3, the rules of data validation. Let's see how computers actually fight back against our clumsy human fingers. Now, before we get into the specific rules, it is vital to clear up the difference between validation and verification. They sound identical, but they do totally different things. Data validation is done by the computer to ensure input data is reasonable and follows strict predefined rules. Data verification, on the other hand, is usually done by humans, like double-checking your typing to ensure the data is actually true and consistent. Simply put, computers validate the rules while humans verify the truth. Okay, here is your cheat sheet for the strict rules these systems use to act as bouncers at the database door. A presence check ensures you didn't just leave a required field blank. A fixed value check means you have to pick from a specific list, like M or F. A type check stops you from typing words into a numbers-only box. A range check makes sure an entered age is actually, say, over 12. Length checks demand exactly 8 digits for a phone number. And format checks, those insist that your email address actually contains an @ symbol. We have all felt the pain of an application form just absolutely yelling at us in angry red text. That happens when those exact validation rules we just talked about catch us slipping up in real time. The system actively rejects the garbage before it can even touch the database. Thankfully, though, designers don't just rely on angry red text. They use clever user interface tricks like drop-downs, radio buttons, checkboxes, and date pickers to make validation basically painless. By forcing us to select from valid options right from the get-go, they completely prevent errors before we even make them. Moving to step 4, check digits and parity bits. Let's get into the secret mathematical handshakes data needs to pass for even tighter security. Okay, let's walk through this one together. Take the calculation for a Hong Kong identity card, for instance. That letter or number at the very end of the ID, it is not random at all. It's a check digit. It's the result of a very specific, weighted algorithm applied to all the preceding numbers. By multiplying each digit by a specific weight, adding them up and doing some division, the system mathematically proves the entire number string is valid. It's a brilliant, automated way to catch typos in long ID numbers. So that handles human-readable numbers. But what about when computers are talking directly to each other in pure ones and zeros? Can they really catch every single glitch during transmission? To solve this, computers use a parity check. Essentially, the system counts up the total number of ones in a piece of binary code. Then, it slaps a parity bit onto the very end to ensure the total count of ones is always even or always odd. If a single bit flips during a network transfer, the parity breaks, and the computer knows the file is corrupted. Now keep in mind, it's not a perfect shield. If two errors happen at the exact same time, they could cancel each other out, and the flawed data would unfortunately sneak right through.
And finally, step 5, storing and accessing data. Once our data survives that intense gauntlet of rules and math, where does it go?
Well, it settles into its physical home, and how we get that data back depends entirely on where it lives. There is a stark contrast in access speeds here. Older formats like magnetic tape use sequential access, which is super slow, kind of like fast-forwarding a cassette tape to find your favorite song. Compare that to the lightning-fast direct access of modern hard disks and USB drives, which can instantly pinpoint exactly what you need without having to scan through everything else first.
So, with all these invisible rules, these strict validations, and high-speed retrieval systems guarding our digital lives, it leaves us with one pretty wild thought. If a computer perfectly validates a lie, say a beautifully formatted, mathematically flawless, but entirely fabricated ID number, who is actually responsible for the truth? Because computers, they are absolute masters at validating the rules perfectly, but it's still up to us humans to verify reality. Thanks for joining me for this explainer, and hey, I bet you'll never look at a basic online forum the same way again.